So everybody can ask questions, can unmute herself or himself and ask questions without any need to use the Q&A session. So we thank the Simon staff for helping with this. Now, the first speaker of today will be broadcasting from the coast of the Mediterranean. This is Emanuel Milman from the Technion. And the title of his lecture is Sharp Isoperimetric Inequalities for Affine Quermassintegrals.
Yes,
please, Emanuel.
Great. Thank you very much, Boaz. I think you can hear me, yes. It's a pleasure to speak at this conference, and thank you for the organizers for the invitation. Everything I'm going to talk about is joint work with Amir Yudayev, also from the Technion. Although I'm not quite sure it fits perfectly into the theme of concentration of measure phenomenon, I'll do what I can, and maybe towards the end I'll mention something which is maybe more in line with the interest of the workshop. Okay, so let me start. But now it doesn't move. Very strange. Okay, so let me start. So just recall our setup. We have a convex body, capital K, in Rn. So by convex body, I mean a convex compact set with non-empty interior. And the classical fact dating back to the 19th century is that if I take my convex body K, and setwise add to it a Euclidean ball of radius t, so t times b2n, the Euclidean ball, and I take the volume. So essentially anytime you see absolute values in this talk, I mean volume and the or Lebesgue measure and the underlying affine hull spanned by the set. Let's see if I can see myself. Yes. Then this volume turns out to be a polynomial of degree n in the variable t. And the coefficients here, modulo some normalization, the coefficients are called the kth coefficient here is called the kth Quermass integral of capital K. So there's capital K, there's little k. I'm sorry for the notation, but that's the way it is. Sometimes these are called intrinsic volumes. Okay, so this is not a very explicit way to define them. There are various other additional ways. One can use a formula in differential geometry by integrating various curvatures along the boundary of K. For us in this talk, we'll be more interested in an integral geometric formula for these Quermass integrals, given by Kubota's formula. And this is it. So up to some normalization, basically what you do is the following. To compute them, you integrate over G and K, where G and K for the rest of the talk is the Grassmannian of all k-dimensional linear subspaces of Rn. Okay, so this thing is a homogeneous space. The orthogonal group acts on it transitively, so it carries a Haar measure. And we denote the associated Haar probability measure by sigma. So basically, this integral just means that you take a uniform, randomly sampled k-dimensional linear subspace, F, you orthogonally project K onto F, and you take the k-dimensional Lebesgue measure, the k-dimensional volume, and then you just take the expectation. Okay, so just the average projection onto a k-dimensional subspace. So for instance, let's see a couple of examples. So the n-1th Quermass integral, it's actually easy to see what it is from this formula. It's basically the linear coefficient in t. So it's basically the first derivative in t. So the first derivative of volume under addition is just surface area modulo some scaling, and that's exactly what this guy is. Okay, it's the surface area. On the other extreme, if you test the W1, the one Quermass integral, then it's easier to see what happens in this formula. So basically, you project over all possible one-dimensional directions, and you calculate the one-dimensional length of the projection. So this is basically the width of the body in the direction. So what you get after some normalization is basically the average width, the mean width of the body. Okay, so these Quermass integrals or intrinsic volumes are very important and cornerstone parameters of which you can associate to any convex body. And the classical fact is the following: if you fix K from 1 to n-1, so the other cases 0 and n are not very interesting. The classical fact, which I think is due to Alexandrov, but maybe quite possibly even before, is the following sharp isoperimetric inequality for these Quermass integrals. the kth Quermass integral for any convex body K is lower bounded by whatever happens to a Euclidean ball having the same volume as capital K, which I always denote from here on as B sub K. So the B sub K is just a Euclidean ball having the same volume as K. So this is a sharp isoparametric inequality with equality if and only if K is a Euclidean ball itself. Okay. So for instance, when K is equal to n minus 1, this is a sharp lower bound on the surface area. So this is a genuine isoparametric inequality for the surface area for convex sets. And for K equals 1, this is a sharp lower bound on the mean width of the set. And this is called the Urysohn's inequality. Okay, so this is a completely classical fact. And this is the starting point of our work. Because back in the 80s, Erwin Lutwak defined the following variant on these classical Quermass integrals. He defined the kth affine Quermass integral as exactly the same thing. Now we denote these by phi sub k. Okay, it's exactly the same thing as before. One takes the L minus n norm in this integral. Okay, and why are they called affine? Because as it turns out, this was shown by Eric Greenberg, these guys are indeed invariant under volume-preserving affine transformations of the convex body. I'll just say for short, affine invariant. Okay, so these turns out to be affine invariant, and as such, they are the central pillars of affine convex geometry, which is the study of convex bodies modulo the group of affine transformations. Okay, these are completely fundamental parameters.
Emanuel, may I ask you
and also in the 80s.
Yes. Emanuel, can you say a few words why? Can you say a few words about the proof that they are invariant under volume-preserving transformation? It does not look completely obvious.
Well, that's yeah. Okay, so I think the origins go to an observation of Furstenberg and Zucconi, which is a dual observation, which is an identity that they discovered for ellipsoids. But the proof is really, a combination of differential geometry with a little bit of Lie algebra. So I cannot really give you intuition besides the fact that there's only one power which makes it a affine invariant, and that's minus n. Okay, you have to look at the volume element and do the computation.
Well, but so can't you just use? Can't you just write the DF and check how it changes in the affine transformation? Because it's, you can express in terms of support function, you have support function changes and you have the dual vector. Like, can't you do just that? The usual.
I agree that it's a computation. It's a computation. It's not very easy, actually. It's not elementary, but you're welcome to do it in any way that you can. Okay, so anyway, these are affine invariant, and the natural conjecture posed by Erwin is that they should satisfy the same sharp lower bound, the same isoparametric inequality as before, but now since things are affine invariant with equality if and only if K now is an ellipsoid, not a Euclidean ball. And of course, by Jensen's inequality, the L minus n norm is smaller than the L1 norm. So this is harder, should be harder. And in fact, this is exactly the right power to make things affine invariant. So this will be a strengthening, an affine invariant strengthening of the classical case. Okay. So that's the conjecture. Now, let me note that the rank 1 cases, by rank 1, I mean the rank of the corresponding Grassmannian. So the cases K equals 1 and codimension equals 1, K equals n minus 1. The rank 1 cases of Lutwak's conjecture are completely classical. So I'll show you in a second. Before, let me just recall some standard notation. We denote by hk of y the support function of the convex body K in the direction of y. This is a one homogeneous function. Okay, just the width in given direction y. And also the polar body is just the unit ball of the dual norm associated to K. So if you want, this is just the one level set of the support function. Okay, so now let's check the case K equals 1 of Lutwak's conjecture. I claim this is exactly the Blaschke-Santalot inequality. Why is that? Well, if you project onto a one-dimensional direction spanned by theta, what you get, as we said before, is just the width in the direction of theta plus the width in the direction of the antipodal direction, right? Now, by using a very elementary and standard formula of calculating the volume of a body by using polar integration, what you have to do is you have to, if you want to calculate the volume, you have to raise the radius to the power of capital N. First Quermass integral, which is the integral of this to the power of minus n, is up to some normalization. It's exactly the volume of the polar body to k minus k, because we're adding k in the antipodal direction. Okay, so that's an elementary computation. So if k is origin symmetric, then k minus k is just twice k. So, the factor of 2 just pops outside, just changes normalization a bit. And you see that Lutwak's conjecture is exactly equivalent to the statement that the volume of the polar body to k is now upper bounded, because we didn't raise it to a negative power. So now it's upper bounded by the volume of the polar body of the Euclidean ball having the same volume as k. Okay, that's the conjecture. And if you reinsert the dependence on the volume inside, you get that the volume product of k and its polar is upper bounded by whatever happens to the Euclidean ball. And that's exactly the celebrated Blaschke-Santalot inequality, which is just cornerstone of convex geometry. For general k, one has to be a bit careful, because the Blaschke-Santalot inequality, now it's important with respect to which point you take the polar body. So if you take the polar body with respect to the so-called Santalot point, which is the point for which this volume of the polar is minimal, then this is called the Blaschke-Santalot inequality. And you can check that this is slightly stronger than Lutwak's conjecture, but both are of course true. Okay, so k equals 1 is Blaschke-Santalot. I should mention historically that the equality case in the Blaschke-Santalot inequality for regular enough convex bodies was established already by Blaschke and Santalot. For general origin symmetric bodies, this was done by Saint-Ramon. And for general bodies, this is due to Petit. Okay, so this is the case k equals 1. The other rank 1 case is the case k equals n minus 1. And this is exactly what is called Petty's projection inequality. Let's see why. So in this case, you have to project to a codimension 1 hyperplane perpendicular to theta. And it turns out that the volume of this guy, if you extend it as a one homogeneous function, is a convex function. So it's the support function of some, I think this is due to Minkowski actually. So this is the support function of some convex body, which is called the the projection body of k, pi of k. And this, so if you look at the polar body, which is denoted by pi star of k, then it turns out that the n minus 1 affine Quermass integral is up to some normalization exactly equal to the volume of this polar projection body. So this means that Lutwak's conjecture is exactly equivalent to the following sharp upper bound on the polar projection body of k. And this is exactly what Petit proved. Okay, this is Petty's projection inequality. Again, a completely classical inequality in convexity. So these cases are well known. And I should mention that, of course, after the original proofs of these inequalities, various people have contributed and extended these results. So this is just a partial list: Campi, Gronchi, Lutwak, Mayer, Pajot, Reisner, Yang, and Zhang. And I apologize if I missed anyone, which I surely did. Okay, so these are the classical cases. Some related results regarding Lutwak's conjecture. So it has been shown by Powers and Pivovarov that if you're not quite going after the sharp result, then using methods from asymptotic geometric analysis, you can get the result up to some constant, strictly smaller than 1, to the power of k. So this was known. Another related result concerns the dual theory. So it turns out that in the Minkowski theory, everything in the primal theory has a dual version where you replace, in the dual version, one replaces the operation of projection by the operation of intersection. And in this case, it turns out that you need to replace the power of minus n by the power of plus n to get an affine invariant quantity. This was also verified by Eric Greenberg. And then you get an affine quantity again, which is called the dual affine Quermass integral, phi tilde. But for the dual theory, usually things are easier. And indeed, it was shown by Boozman and Strauss and reproved by Greenberg that you do have the dual sharp isoparametric inequality. Now the lower bound becomes an upper bound. with equality if and only if K is an ellipsoid, at least if K is larger than 1. And I should mention that Richard Gardner, they showed this result for convex sets. Richard Gardner extended this result for arbitrary bounded Borel sets. And then the equality cases are much more delicate, okay? But this is in the dual theory, okay? I should also mention, going back to the primal affine Quermass integrals, we're interested in lower bounds, but of course, upper bounds are also very interesting. And here, even the classical case, at least for the reverse inequality to Blaschke-Sandalo, this is the celebrated Muller's conjecture, which, I could devote a whole talk just on this conjecture, so let me not do that, but, it's wide open in dimension 4 and higher. Just very recently, it was resolved in dimension 3 for origin symmetric sets. Remarkably, I should mention that the other rank 1 case, the case K equals n-1, is actually known. The sharp upper bound is known. This is due to Zhang, who showed that the upper bound is attained whenever K is a simplex. So that's quite remarkable. I think actually for origin symmetric convex sets, the sharp upper bound is not known. Of course, it's conjectured to be a parallel, so an affine image of a cube. But I think that's not known. But anyway, in this talk, we're interested in lower bounds. And basically, the higher rank cases beyond the classical cases have remained wide open since the 80s. I'm not even familiar with a single partial result.
Emanuel, can I ask you a question?
Yes, I remember.
In the upper bounds, is there any moral reason why the case K equals n-1 is easier than the case K equals 1?
That's the $1 million question, right? I know.
Oh, all right. Yeah.
Well, if you manage to do Muller,
no. But what is the moral difference between the different Ks?
This is why I say Zhang result is quite remarkable.
Okay.
I'm going to give you a good answer, except an empirical one. The proof is in the pudding. I don't know.
How does the proof work? Well, maybe this is not a good discussion for now, but
yeah.
All right, I'll let you go on with your talk. Thanks.
Yeah. Okay, so this was what was known, and finally arrived to our results, which, as I said, are joint. Everything is joint with Amir Yudayov. So we fix the convex body K, we fix little k, and our first theorem is indeed resolving Lutwak's conjecture in all possible ranges of parameters with the equality cases, equality if and only if K is an ellipsoid. So that resolves everyone's conjecture. Theorem 2 is a strengthening of theorem 1 and immediately implies theorem 1. Basically, we show that anytime one applies Steiner symmetrization in a direction u, then the affine Quermass integral can only go down, can never go up. So what is Steiner symmetrization? So here's a very nice graphic I downloaded from the internet. Basically, so here in this graphic, don't use u, you use theta. So what you do, so you look at theta perp, this codimension 1 hyperplane. Okay, you look at a one-dimensional fiber over each point. So this intersects K by convexity in a one-dimensional interval, and you just translate this interval until it's symmetric with respect to its base point on theta perp. Okay, and you do this for each point. So of course, by Fubini's theorem, you preserve the volume, and moreover, it's very simple to see that you preserve convexity, so you still get a convex body, and it's a classical result dating to the end of the 19th century, beginning with the 20th century, that for any convex body, in fact, any compact set, you can find a sequence of directions ui, so that if you apply Steiner symmetrization consecutively in the direction of u1, u2, and so on, then your convex set will converge in any possible topology that you like to a Euclidean ball having the same volume. So volume is not lost in this procedure. So therefore, theorem 2 immediately implies theorem 1. Okay. So this is a first strengthening of theorem 1. Second strengthening is given by theorem 3, which states that not only are ellipsoids the only global minimizers, unique global minimizers of phi k, but they're actually the only local minimizers, again, with respect to any topology that you like. They're all equivalent. Okay. These are our results for this talk. I should mention, let me go back to the classical cases, the rank 1 cases. So certainly this inequality The inequality here has been previously known, for sure. However, the equality cases are actually quite delicate. So in the case k equals 1, the Blaschke-Santalo case, the fact that standard symmetrization decreases the, increases the volume product. In the origin symmetric case, this is due to Meyer-Pajor and Lutwak, and I think in the general case, this is due to Meyer and Reisner. So this was known. By the way, when I say equality case, maybe I should explain. When I say equality, I mean so let's assume that you know that for any direction u, the standard symmetrization has the same affine Quermass integral as the original body. So you cannot find a single direction when it's decreased. Then it must be an ellipsoid. This is what I mean by the equality case. So this follows from, in the Blaschke-Santalo case, this was known. But however, in the Petit case, it seems to us that this is actually new, this observation. So even there, I think we managed to do something new. And what about theorem 3, the local minimality? This was just recently established for Blaschke-Santalo by Meyer and Reisner, in fact, for the volume of the polar body around the Santalo point. But again, for Petty's inequality, this again appears to be new. Okay, and the fact that k equals n-1 is harder is actually in line to our own investigation. So in the equality cases, we treat all the cases in one fell swoop, no problem. However, the case k equals n-1 requires additional work. So we need an additional section in the paper to handle that case. So this case does seem harder.
So Emanuel, knowing that the ellipsoids are the only local minimizers, yeah, is it possible to set up some kind of gradient flow on the space of bodies?
Right. So we tried many things. Standard symmetrization is of course very natural, and there's we used at the end a continuous version of standard symmetrization, but I'm not familiar with an interpretation of this as a gradient flow. Of course, if you, in fact, I'm not sure I know a lot of I'm not sure I know proofs of classical results in convexity by doing what you suggest as a gradient flow. That would be very, very interesting. Of course, there are various, there are various geometric flows like mean curvature flow and their distant cousins, which can produce some of these classical results in convexity. At some point, we even, dared to try to do it for this problem, but we don't know how to do it. Certainly, there are some flows which are affine invariant, mostly with respect to affine surface area. So I think there are proofs, maybe by Ben Andrews and others, of the affine isoparametric inequality for convex sets by using a certain curvature flow, which is affine invariant, but nothing of the sort that you suggest. That would be super interesting.
Also, Blaschke-Santalo. Andrews' proof also gives Blaschke-Santalo.
Sure. Yeah. Okay, so these are our results. So let's try first attempt. Let me go quickly because this doesn't work, but just to see what you can do. Well, you can say, well, come on, I can prove this problem. Let's just do the 2 codimensional case, k equals n-2. And of course, the first idea you have is let's do double integration because we can, what does it mean to select a random n-2 dimensional subspace? I can first select a random 1 codimensional subspace, call it E, and then take a random 1 codimensional subspace of E, which we get F. Okay, and let's try to calculate this integral. Of course, you can apply Petty's projection inequality to the inner body, but the problem is this body lies in dimension n-1 now. So you cannot. You would like to calculate this integral for q equals n, but we can only do it for n-1 here. If you want to apply Petty's projection inequality, and by Jensen's inequality, you can do any q which is smaller than n-1. That's not a problem, but you cannot go above. That would be false. So if you apply Petty to the inner body, then you get something only involving the volume of this inner body, which is this. And then you can apply Petty again and get something only involving the volume of the body. And you don't really need to keep track of the constants because along all the inequalities, we had equality for Euclidean ball. So in other words, what we are able to show using this approach, very simple approach, is this inequality that's completely trivial using Petty. However, we don't get the right power. We want to get the power of minus n, we get the power of minus n-1. And you can do exactly the same thing for general k-dimensional subspace. We're going to get the wrong power. We want to get minus n, we get minus k plus 1. So we lost the affine invariance, doesn't work. And in fact, we had at least a dozen additional approaches, all of which always hit this barrier. We can beyond this power in like a dozen different approaches. And at some point, we even thought that maybe that's really the truth. You cannot do better than that.
Emanuel, does
yes.
it imply the result of power is Simple-Avarov?
So of course, I mean, the result is up to a constant to the power of k. We get a constant of 1 with the characterization of the equality cases. Oh, you mean this?
No. Yeah.
You mean just this? Yes. We can do something like that, but I mean
Okay. Mm-hmm.
Okay. So why is this so challenging? Okay, let me try to explain. I don't know if I can, but we've worked on this on and off for several years, and just this year we had finally a success. So how are the rank 1 cases proved, at least classically? So what you do is you associate to your convex body K an auxiliary convex body. This will be either the polar body or the polar projection body. Let me call this auxiliary body LK. Apologies to the slicing people. And it lives in Euclidean space Rn. And what does this body do? It encapsulates the function we're really interested in, okay, in a certain way. Turns out that in the classical cases, you just have to calculate the volume of this body to get what we're interested in, the affine Quermass integral in those cases. And the point is to show that under Steiner symmetrization, the volume of this auxiliary body can only increase. Okay, so the inequality gets reversed. That's not a big deal. This is so how is this body obtained? In both of these cases, it's obtained by identifying our Grassmannian with real projective space RPN minus 1, which is just the sphere with antipodal points identified. How do we do this? Of course, in the one-dimensional case, we'll just intersect the sphere with a one-dimensional line. In the one codimensional case, intersect with the perpendicular direction. So this identification is trivial. And then we basically get a function which is defined, an even function defined on the sphere. So you can extend it to the entire Rn just by taking a one homogeneous extension. And if we take its level set, we exactly get these bodies, either k-polar or the polar projection body. And then it remains to see what happens under Steiner symmetrization. The problem with the higher rank cases is that we no longer have this identification. So it's not, so of course, the Grassmannian in the higher rank case, you can embed it in R capital N for a large enough N, but you either have to use a very large N and then this embedding is highly non-injective, or you can use a small capital N, but then the embedding is nonlinear. So you lose something, and really we tried both, well, at least the first approach, and nothing seemed to work. And in particular, it wasn't clear to us in which space should our auxiliary body reside, because you cannot do it in the same dimension anymore. And at the end, our solution was that first of all, we do not know how to construct such a universal body. In fact, our auxiliary body will depend on the direction U in which we're performing the Steiner symmetrization. And secondly, this body will reside in a vector bundle over the lower dimensional Grassmannian. Okay, so you don't have to worry about these fancy words. The construction will be very simple, but this kind of resolved in which space should the auxiliary body reside. As a small price, instead of taking the Lebesgue measure and showing this inequality as before, we're not going to use the Lebesgue measure and this vector bundle. We're going to use a slightly modified measure, mu sub u. Okay, and that's kind of a very high-level description of what we're going to do.
What does it mean, a convex body in a manifold? You mean geodesically, or is convexity not important anymore?
Yeah, well, I didn't say this auxiliary body will be convex.
Oh,
but,
no, it says convex body.
That's just the case 1 and minus 1.
Right.
Okay. So just in this case, it was convex. We will see that in our case, it will be also convex in an appropriate sense. Okay.
Mm-hmm.
So without further ado, let me show you the construction of this auxiliary body, which we call the projection rolodex. Hopefully this name will be suggested. So first of all, some notation. If I have a k-1 dimensional subspace E in a point X in Rn, let me denote think this is a very suggestive notation, this projection onto E wedge X and taking absolute values. So basically what we do is we want to take the k-dimensional Lebesgue measure of the projection of K onto the span of E and X. Generically, this will be a k-dimensional subspace. Okay, but we want to make this into a one homogeneous function. So we also multiply by the length of the projection of X onto E perp. Okay, so if X is perpendicular to E, then this is just a trivial one homogeneous extension. Okay, so in most cases, X will be perpendicular to E. Okay, so having this notation, let me define what we call the E projected polar body, L sub EK. So this body lives in E perp, and it's basically the one level set of this function. Okay, we only consider X and E perp because movement of X parallel to E doesn't change this function at all. So this function has a trivial product structure. We just want to see the non-trivial, throughout the trivial factors. So we only consider X and E perp. So a little lemma, which I'll leave to you to check. I don't know if I'll have time. Actually, I'm running slow. This guy is always convex in E perp. Okay, so this answers something about convexity. Let's just check what happens when E is the trivial subspace 0. Okay, then, well, this function is, you just basically project to dimension 1. What is the projection to dimension 1? As we said before already, it's the support function in the direction of X plus the support function in the direction of minus X. So this is exactly, just as before, the polar body to K minus K. So this guy is trivially convex. Okay, but this is always true. This guy is always convex. Here comes our definition, which we call the projection rolodex. So basically, it's a collection of all tuples. E is a K-1 dimensional subspace of U perp. So this is going to depend on U. And X is just an element of our E projected polar body. So in this sense, this body is convex. And the reason we call it projection rolodex, I hope you guys remember what was the rolodex before the invention of the cell phone. It was this kind of, table, a collection of these notes. So so each of these notes is basically this polar body LEK, and they're kind of arranged and indexed by this lower dimensional Grossmanian. Okay, I hope the name is suggested. Note that this projection rolodex encodes this function. Okay, why? Let's see. So take a generic k-dimensional subspace F and intersect it with U perp. Okay, and call this guy E. Generically, this will be a k-1 dimensional subspace, right? So this is okay. We still have one additional direction to choose. Let's call this the orthogonal direction given by theta. So theta is an element of the sphere perpendicular to E. Okay. And what does it mean to be inside LEK? What does it mean? So T theta is an LEK. So this is just one homogeneous function. So T pops outside. So this happens if and only if T times the volume of the projection of F of K onto the span of E and theta, which is F, is at most 1. So this means that the radius in which we can go in the direction of theta is 1 over the volume that we're interested in. So this means that you can read off this volume that we're interested in as just the norm in the direction of theta associated to this LEK body. So really, the information that we're interested in is contained here. Yes?
Is it a good idea to think about this projection rolodex as just family of projection bodies with respect to various subspaces? That's the way you think about it? So on each page you have a projection body of the dimension. Am I right? In each page you have a projection body of the projection to the one-dimensional up subspace. I mean, right? If you so each slide. Okay, thanks.
That's another way. Yes. Okay. I'll just heads up to the organizers. I will aim for the 55-minute mark because I've been asked questions. Is that okay? Or yeah. Okay. Yeah, so the second ingredient we need is the Blaschke-Petkanchi type formula, which you can find in the beautiful monograph by Schneider and Weil. And from now on, we fix the direction U. always be fixed. And this Blaschke-Petkanchen type formula says that if you're interested in integrating a function f with respect to the Haar measure on G and K, so up to some normalization, this is the same as doing the following thing. So first of all, you can select a k-1 dimensional subspace of U perp, okay? But then you still need to select a direction on the sphere with respect to E perp. But if you just do this randomly and you calculate the integral, you'll get the wrong answer because there's a Jacobian factor here, right? And it turns out that the right Jacobian factor is this guy in red. You have to amplify by the cosine of the angle of your theta k with respect to the direction u raised to this power. And the intuition is, well, if you do this just randomly without any weight, you'll be giving too much weight to subspaces which are close to the equator. You want to penalize them, and you want to give more weight to subspaces which are closer to the North Pole, to U. Okay, that turns out to be the correct answer. But as a corollary of this formula, if we define the measure mu sub u to be this is just the Lebesgue measure on this vector bundle that I mentioned. Just you select E to be a random subspace of U perp. You take the Lebesgue measure on E perp, and you multiply by the Jacobian. Then it's immediate to see that it's a very simple calculation, but I think I'm out of time. It's a very simple calculation to check that the mu measure of this projection rolodex is up to some normalization exactly the integral that we're interested in. Okay, I actually wrote down the proof. It's basically doing polar integration after you pass to E perp. Okay, and this Jacobian factor exactly makes things so that the power that you get here is n. It's a very simple computation, but I think I'm running low on time, so let me skip this. Okay, but this is really the full proof, and this is being recorded, so you can check it out later. But it's a very simple computation based on this Blaschke-Petkanchen formula. Okay, so with this in mind, what is our goal? Our goal is to show that, and by the way, I didn't say, but I'm only going to show you an idea of how to prove the inequality. I'm not going to talk about the equality cases at all. The big breakthrough for us was showing finally the inequality, the sharp inequality here. And once you do this, then if you have equality here, you can start looking at all the equality cases. What does it mean? It certainly requires more additional work and some new ideas, but this is already something that you can work hard and do. But the idea of showing the inequality was the big kind of breakthrough for us. So I'm only going to talk about the inequality. So how do you show that standard symmetrization can only decrease this guy? Well, as I just showed to you, it's the same as showing that the mu measure of our projection rolodex can only increase under standard symmetrization, right? Because this guy is the same as this modulo some normalizations. So this is going to be our goal. And notice, and this was the key thing for us, that now everything is aligned with you, right? The direction of the standard symmetrization, the definition of the projection rolodex, and the measure mu, they all depend on you. Okay, and in fact, we're going to need to apply one additional last alignment. So how are we going to prove this? When you calculate the mu measure of this projection rolodex, so you integrate with respect to, this is just you select your random subspace E in U perp, you take the Lebesgue measure on E perp, but remember that E is perpendicular to U. E is in U perp, so this means that U is an element of E perp. So when we integrate over E perp, we just apply Fubini. We first integrate in the direction of U, and then we integrate over everything else. And this is the last alignment that we need. And this is quite convenient because then you see that the angle with U is just given by S, where S is the height along the direction of U. Okay, so this guy, this scalar product just becomes S, and we see that we get S to the power of k-1 outside. And what we have left is we have left just the volume of this body indexed by this level set. Let me give this a name. Let's call this body LEUS of K. So this is just the section of our E projected polar body, which is parallel to U polar at height S. So the idea is to fix the height and integrate just over that section. And we just have to calculate its Lebesgue measure now, just its volume. Okay. And now, now it remains to show. So the whole idea was to pinpoint where does the standard symmetrization do. So now it remains to show the key inequality that for this body, Steiner symmetrization, once you fix the height S, Steiner symmetrization can only increase its Lebesgue measure. Okay, so basically what you see on this slide was the key idea. Okay, was to pass to the projection rolodex to this measure and to make one final alignment, and then it remains to show why Steiner symmetrization increases the volume of this body. Okay, so we need a bit of convexity. How am I doing on time? Okay. So let me introduce some notation. Let me denote by A superscript Y the one-dimensional section of A in the direction of U over the point Y in U perp. So just the one-dimensional section, okay? And let me use R sub U to denote the reflection about U perp, okay? So what we're going to do is we're going to introduce a very simple continuous version of Steiner symmetrization. So we have this one-dimensional interval K superscript Y, and we have its reflected version. So let's just use a convex combination with weights which sum up to 1. So weight 1 plus T over 2 and weight 1 minus T over 2. Okay, so of course, at time T equal 1, we just get the original body. At time minus 1, we get the reflected body. And at time 0, we get exactly Steiner symmetrization. Okay, in fact, this makes sense for values of T which are outside this interval minus 1, 1. But then these guys are, one of these guys is negative. And remember, we're adding sets. So this guy actually is no longer, so for instance, volume is no longer preserved when you're outside this interval, but this makes sense. You can still do this. And in fact, this is a very particular instance of what is called a shadow system. So I don't want to get into that, but if there are some experts in convexity listening in, this is a very particular, I think this is called Minkowski linear shadow system. But all of our results in this slide apply to general shadow systems. So the key inequality, the key, where does convexity come in, is in the following proposition, which says the following. So you fix your subspace E, you fix a height S, that's very important. Then the function mapping Y in U perp and T is our time parameter, to this guy. So you fix S, you fix the red, but you allow yourself to move, to deform your body, to make a continuous Steiner symmetrization, and to move Y. The claim is that this function is jointly convex. Okay, that's the claim. It's very simple to see that it's even, because it's even. So if you flip simultaneously the sign of Y and T, then it's very easy to see that this function remains the same, because if you flip the sign of T, basically what you're doing is you're reflecting your body. Okay, so calculating the volume of the reflected body onto a subspace is the same as calculating the volume of the original body to the reflected subspace, right? But the reflection, our U of E doesn't do anything because U is perpendicular to E. So reflection of E doesn't do anything. The only thing that happens is you change the sign of S when you reflect with respect to U. But changing the sign of S is the same as keeping the sign of S and changing the sign of Y, because it's just the antipodal point. So you don't change the span. So this function is very trivially even, but the point is that it is convex. Okay, and how are we going to use this? We're going to use this because this means if this function is jointly convex and even, this means that its level set, which I wrote here, its level set is a symmetric convex body, obviously. Okay, let's give this body a name, L tilde EUS. And again, we're only interested in what happens inside E perp, because if you change Y by something parallel to E, then this function remains constant. So we might as well intersect with E perp. So we have this, so assume that we show this. So this means that the level set is a symmetric convex body. Notice that the T section, the section of this convex body at height T, is just by definition the body that we're interested in. And now it remains to use the classical fact that if you have a centrally symmetric convex body, this axis is the t-axis, then the volume of the central section is always larger than the volume of any other section. Okay, so this is written here. This is exactly what we want to show. And this is exactly what's written here, because the central section is exactly Ku at time 0. And this section is Ku at time 1. Why is this? This is just the obvious trivial argument that I'll just remind to the audience. So basically by convexity, we know that the central section contains, by convexity, the 1/2 interconvex interpolation of the section at t equals 1 and at t equals -1. But due to symmetry, these sections are exactly the same, just with a minus sign. Okay, but then if you apply Minkowski inequality to both sides of the inequality, you will get what we wanted. Okay, so at the end, of course, there's convexity and there's Minkowski in the background, but the whole point was to pinpoint where it is. Okay, so once you have, so I hope I managed to convince you that once you have this proposition, you are done. And in fact,
it wouldn't be easier to have some functional version like the Braskamp-Leib, similar to how Campi-Gronchi do that. Like you can't like, instead of using Brun, to see what I'm.
No, well, this argument is trivial. I don't know what to say. I mean, just this part. If you have a simplified proof of our result,
Never mind.
Yeah, no, but this is just telling that the volume of the central section is, it's a monotone function. It's an even function of t, which is monotone decreasing.
No, I'm not saying it's not a simple fact. I'm saying like if one could avoid the use of auxiliary bodies. But yeah.
I don't know how to do that. Okay. Okay. So this is the key proposition. I'm not going to show you a proof. Let me just very quickly, because I do want to get to something else. I wasn't planning on showing you a proof, but I'll just tell you the idea. We actually, this wasn't the hard part, okay, showing the convexity. We actually more or less knew about the convexity. The hard part was, aligning everything with you. So, if I give you this exercise, show the convexity, if you believe it's true, then you will work and you'll show it. It's not, but so we actually have several alternative proofs of this fact because each version had its own advantage. We needed a certain version to prove theorem 3 about the local minimality. But anyway, the idea, which is common to all shadow systems, is that actually you can realize this volume of the projection of KUT as the projection of a body K tilde living in one dimension higher. Okay, so that's the rough idea. And the point is you have to fix S, because when you project this higher dimensional body K tilde, you get an expression which is actually, when you fix X, it's an affine function of Y and T, but it's a nonlinear function of S with T. So this is why you really have to fix the height S. Okay, so I'm not going to show you this proposition because in my last so basically this is kind of the sketch of the proof that I wanted to show you. And everything else is you can try to do by yourself, but basically you have the whole idea. I do want, in my remaining 5 or 6 minutes, I want to say something a bit very simple but related. Okay. So you can do, so now let's go back to our definition of the Quermass integral. We used, of course, minus n in this entire talk, but you could use the LP moment Quermass integral, which we know by the scalar graphic Q. Let's use the LP moment here. And of course, the case P equals 0 is interpreted in the limiting sense as some type of geometric average. So the case P equals 1 is the classical case, the classical Quermass integrals. The case P equals minus n are the affine Quermass integrals. And the case P equals -1, these are also, this case has also been studied by Hadwiger and by Erwin Lutwak. This is called, for obvious reasons, the harmonic Quermass integrals, because you're kind of doing a harmonic average. So as an immediate corollary of our main result, just by applying Jensen's inequality, if you manage to prove lower bound for minus n, you'll be able to prove a lower bound for P, for any P larger than minus n. And the claim is that you have the same sharp isoparametric inequality for these pth Quermass integrals, but now you lost affine invariance, so you have equality if and only if K is a Euclidean ball. I should mention that the case P equals -1 was already proved by Irwin. That's not new, but going all the way down to -n, maybe that is new. And I should mention, why do we stop at -n? Maybe you could go below. No, the inequality below -n is simply false, even for ellipsoids. That would be just false, because you'd have to use Jensen's inequality going in the wrong direction. It would be at strict inequality, and you'd be dead in the water. So really P equals -n is the last and the sharp affine invariant exponent which you can use. The last thing I want to mention, this is my last slide, is a relation to a Loomis-Whitney inequality, which maybe is more interesting to this community, which I know there are many computer scientists in the audience, and Loomis-Whitney is used a lot. So what is the classical Loomis-Whitney inequality? It states that for any compact set K, if you take the projection onto the n-1 dimensional principal hyperplanes, okay, you take the product of these volumes, then this is at least as large as the volume of K to the power of n-1. This gives you the right units. And as Loomis and Whitney remark in their paper, for any reasonable set K, its surface area is always going to be at least twice as large as a projection to any hyperplane, right? Because surface area element just decreases, and for any reasonable set, you're going to hit this hyperplane at least twice from either side of K. So this is true certainly for convex sets, for many other sets. So you might as well take a geometric average, okay? Which means if you apply the result, which means that the surface area of K is at least as large as twice times the volume raised to this power. So this is an isoparametric inequality for K, but it's not sharp. It's with the wrong constant here. But it is, it already gives you a sub-level inequality if you want, and so on. So this is nice. And of course, by reverse induction, you can also get this version. So instead of taking a all principal one codimensional subspaces, you can take all principal K dimensional subspaces, okay, project onto them, take the product, and you'll get that this is larger than the volume of K raised to this power. And in all of these inequalities, you have equality exactly for a box whose axes are aligned with your given orthonormal basis. So in fact, the motivating question for us for this entire work, but of course we went in completely kind of other directions after that, is the question was, can you improve the Loomis-Whitney inequality if you average on the choice over all possible orthogonal bases? Because then it's no longer sharp, because there's no single box you can claim that you get a sharp inequality, because now there's no distinguished orthogonal basis. So certainly this inequality would still be true if you average, but it will no longer be sharp. So question, what is the sharp inequality and what's the extremizer? So we can easily answer this question now. In fact, we can do it before as well. So if you take a geometric average over all possible orthonormal bases, basically you're averaging over SON here, right? So if you apply a random element of SON to your K-dimensional subspace, you just get a random K-dimensional subspace, right? So what is this integral? This geometric average over all orthonormal bases is just the integral over G and K of this expression, and we overcounted by n choose K, right? Because we had n choose K of elements here. Basically, what you get is exactly what we call the L0 Quermass integral, K0. And by the theorem that we have from the previous slide, and in fact, we could, and this is indeed what we did several years ago, we can just use Lutwak's P-1 result. We don't need to use our full result. By Jensen's inequality, any power which is smaller than 0 would work. So we can lower bound this by whatever happens to the Euclidean ball having the same volume of K. And if you compute and see how this affects the volume, this is what you get. So we get this inequality. And this is a sharp averaged Loomis-Whitney inequality, which now is sharp exactly for the Euclidean ball, because this inequality is sharp exactly for the Euclidean ball. So we have equality if and only if K is the Euclidean ball. And now everything is sharp. The extremal case is the Euclidean ball. So this means that this actually does imply the sharp isoparametric inequality, for at least for convex bodies, which is an improvement over the corollary that Loomis and Whitney had, because they got an isoperimetric inequality with a non-sharp constant. But now this average version does give to you the sharp constant. Anyway, so this is kind of funny. That was the motivation for our work. We discovered that actually Lutwak can do p-1, which is more than enough than what we need. But then, we recalled, actually, Erwin has this conjecture, and we got stuck on the conjecture. And then at the end, we're very happy to be able to resolve it. Anyway, so this is all I wanted to say. Thank you very much.
Thanks, Emanuel, for this great talk on an elegant result. We have time for one quick question. Just one, maybe? So we have many questions. Okay, please, Galina.
So I have a quick question, actually. So congratulations, first of all, on this beautiful result. So I was wondering if your argument was written basically and simplified in the case k equal to 1, it sounds like you would get Campi-Gronchi paper. Is that correct? Okay. Now what?
Hold on. No. So after, okay. So as I said, we have, okay. First of all, actually, something which kind of inspired us, or maybe when we had to prove theorem 3, we noticed that we can give an alternative proof of that key proposition, which I did not show you, by actually mimicking the proof, I would say, of Meyer-Peugeot, actually, of Blaschke-Santalon, not Campi-Gronchi. Okay, I would say Meyer-Peugeot was more influential for us, but not because they have the same kind of thing. Because when they calculate the volume of the polar body, they freeze the height s, and they see what Steiner symmetrization does. So actually, if anything, this is similar to that. However, a very crucial difference is exactly what I said before, which is that we need to freeze the direction u. So we always have to work in a subspace which is perpendicular to u. And this is something which is not apparent in any of the previous results or proofs, not in Blaschke-Santalon and not in Petit. So the key, really the key to proving this was to align everything with u and to define our projection rolodex, if you will.
But that's because you use Brun-Minkowski in a subspace rather than Brus-complete functionally. But anyway, but my question was actually, so if you write your proof simply for k equal to n-1, do you get a new proof, shadow system proof of Petit projection inequality? Because I don't know of an analog of shadow system proof of Petit.
Great. Okay, so at the very last subsection of the paper, if you look, we give a new proof of Petit, which is like, two-line proof of Petit, but not this. So of course, we discovered it during our investigation, but so maybe I will answer, I know I'm out of time, but our proof in some sense is taking Blaschke-Santalon and extending it to all k's. We don't know how to prove our result by taking Petit, and we were expecting to start from Petit, from the case k equals n-1 and extending it. We don't know how to do that. There is, so during our investigation, and hopefully this is described well in the paper, there is some type of duality between Petit and Blaschke-Santalon, between k and n-k. There is some type of duality. We don't know how to give a proof of our result from the Petit side, but during our investigation, we found a new, very simple proof of Petit using shadow systems, which is like 2 lines long. Yeah.
I see. Okay, that's that. Okay, you answered my question. Thank you. Great.
Just inequality.
Okay, thank you, Emanuel, again for this talk. I think that we'll postpone the next lecture by 5 minutes. We'll resume in California time, I think it's 10:05. Okay, so Max Pati's lecture will begin at 10:05 in 5 minutes, basically.
Yeah.